Okay, the third experiment that is in your practical manual is the synthesis of aspirin, or also known as acetyl salicylic acid. So it is a sort of like a derivative from the structure of salicylic acid. So the objective is to illustrate the synthesis of the aspirin drug. So the background mainly talks about the aspirin itself. So it is used as a pain reliever, or sort of like analgesic, in which that similar to paracetamol. But here, I think the aspirin is widely used in the US, for example. Okay, it is one of the OTC, or over-the-counter medicine, that they use to treat like normal pain, like headache or having fever or something like that. Okay, but in Malaysia, we tend to use paracetamol. Okay, so the original structure of aspirin, it comes from salicylic acid. So salicylic acid is an example of carboxylic acid, which is this structure over here on the left. Okay, so that is the structure of salicylic acid. So originally, the salicylic acid also have the same curative properties, in which that it can also be used as an analgesic, but then it also has some side effect, because being an acid, it results in some of the patient to have gastritis as well. Okay, so in order to counter that effect, okay, the OH group on the structure that is attached to the benzene ring, okay, has been converted, or we can say that it is undergoes esterification reaction. So as you can see, the OH, okay, has been converted into OC double bond OCH3. So that is actually an ester group. Okay, so this reduce the acidity. Okay, even though it is still carboxylic acid, but it reduced the acidity of the whole structures. Okay, thus giving it maintaining the analgesic effect, but without the side effect. Okay, because as you can see, the structure of salicylic acid, it contain the also the background structure of phenol, whereby you have benzene ring and also OH. So phenol also is known to be acidic as well, slightly acidic. So you have the structure of phenol and also itself being carboxylic acid. So that's why the acidity is higher compared to the structure of aspirin. So now on to the we will look into the reaction first. Okay, so basically there are two ways in which you can achieve the product, which is the aspirin. Okay, so synthesis means you want to prepare a chemical compound or chemical structure, basically in this case organic compound in the lab. So we mix probably compound A with compound B to produce a new product. So the first reaction scheme is the most what do you call that, that will produce high yield, meaning the product form will be in abundance compared to the second method below. So the first reaction scheme have the salicylic acid to be reacted together with acetic anhydride. So acetic anhydride is a derivative of carboxylic acid, which is in this case acetic acid. So the structure actually is two molecules or two structure of acetic acid to be combined together with the removal of one molecule of water. So that's why the name contain anhydride. So anhydride basically means to be lack of water actually, okay? Because when you mix acetic anhydride back with water, it will eventually turn back into acetic acid. So salicylic acid to be reacted with acetic anhydride, and the reaction must undergoes in acid condition. So you see there's a tiny H plus on top of the arrow over there. So that symbolize the reaction has to be done in acidic medium or acidic condition. So the acid used is sulfuric acid, H2SO4, and your product will be formed in which that the OH and also will be converted into the, sorry, somebody is joining, into the ester form. Okay, so you have aspirin, and also 1 mole of this acetic acid actually comes from the acetic anhydride. So acetic anhydride basically contain 2 moles of acetic acid. So one will be undergoing this reaction with aspirin, while the other will be released. Okay, so this reaction scheme, the first one, okay, will provide very good yield. Okay, the product form will be probably around more than 90%. I would say 90%. Sometimes it could be 80%, but the yield will be greater compared with this second reaction scheme over here. You can still have the same product, which is the aspirin or acetyl salicylic acid, by having the salicylic acid with acetic acid. Okay, you can mix these two together. Okay, still in the same what you call same acidic condition, which is sulfuric acid, but the reaction, okay, the second reaction scheme, this reaction is actually reversible, in which that once you obtain this structure over here, this acetyl salicylic acid or the aspirin, it can hydrolyze back into the salicylic acid and also acetic acid. So that's why the yield that you get, okay, or the product obtained will be less. Okay, and most of the time the yield will be around, I would say, less than 50%. You will get around 30% or 40%. Okay, and this reaction, the second one is less favorable, in which so that we prefer to use the first method. Okay, but there's a reason why I put these two reaction scheme together. Okay, so reaction with acetic acid is less favorable. Okay, in excess water, this one. Okay, so since the reaction itself produces water, and also there's an acid catalyst because the reaction is done in acidic condition. So the reaction will go in the reverse direction once the product is formed. Okay, so this is known as the hydrolysis of ester. So since you just form an ester, it can be hydrolyzed back to their corresponding carboxylic acid and also alcohol. So this will cause a significant decrease in the yield, okay, unless, okay, special apparatus is set up in order to remove this water. Okay, because the first reaction over here, there is no water. So the chances of the product to be hydrolyzed back into the reactant is very low. Okay. But if you are doing this in the lab, okay, in campus, you are going to do it in the lab, you will follow the second reaction pathway, which is the second one, okay, because you will use acetic acid instead of acetic anhydride, as this acetic anhydride is class under Jadual 1 by NPRA, the National Pharmaceutical Regulatory Agency, because it can be used as a precursor to produce morphine. Okay, so you can mix heroin together with this acetic anhydride to actually synthesize morphine, which is a recreational. It is a very good analgesic drug, but then again, mainly used as a recreational drug. So that's why our lab doesn't purchase this acetic anhydride. Okay, because if you want to purchase this, it has to be applied through the NPRA channel, meaning through KKM. You cannot simply purchase from chemical supplier directly. Okay, so that's why if you are doing it in the lab, we will use acetic acid. Okay, but I'm talking about the what do you call that, acetic anhydride just now. It is only applicable. The rules is applicable in Malaysia. I'm not sure about any other country whether you can straight away purchase it or not. Okay. Okay. Another method is actually you can prepare the acetic anhydride. We can prepare the acetic anhydride ourselves in the lab, but it is time consuming, and also the yield itself of this acetic anhydride might be low. Okay, because you need to do several reaction first with this acetic acid in order to obtain this. Okay, this reaction you will learn, I think, next semester in pharmaceutical organic chemistry 2. Okay, under the topic of carboxylic acid. Okay, now on to the procedure. Okay, so this is your first synthesis experiment in which that you are going to prepare an organic compound. So the first step is actually to prepare the reactant. Okay, so take 2 grams of salicylic acid. So the weighing process, okay, you can use weighing balance, just a normal weighing balance, or you can also use analytical balance. So if you are using analytical balance, the accuracy will be higher, up to 4 decimal point, and you have to take note of the actual weight, meaning that if you put on the weighing balance, the weight could be 2. Let's say 1. So take note of the weight. Okay, not using this 2.0 gram, because the actual weight has to be used later on in the calculation in order to calculate the yield or the expected amount of product that you should obtain. Okay, so weight 2 grams of salicylic acid, and then place in a 120 ml of conical flask. Okay, then what you do next is to add 3 ml of acetic anhydride, or to be replaced with 6 ml of acetic acid. Okay, and then while swirling or stirring, you have to add 3 drops of concentrated sulfuric acid. Okay, so in this first step, okay, when you mix all of this together, the whole thing will sort of like clump up together. Okay, it won't produce any clear solution or very what do you call that, homogeneous mixture. Okay, that will happen on the next step. And take note over here, if you are using acetic anhydride, it has the ability to irritate your eyes, so make sure you wear safety goggles. And also the sulfuric acid, being an acid, it can cause severe chemical burns, so I would advise you to always how to say, do it in the fume hood. Okay, and also wear glove. Next, on to the second method. Okay, those mixture of reagents that you have in the conical flask, okay, will be heated using a steam bath, or you can also use water bath for about 30 minutes. Okay, this is where you will see the first observation, in which that all of the solid mixture just now will be completely dissolved, and they will form a very clear solution, okay, clear colorless solution. Okay, then what you do next is to remove it from the heat. Okay, remove it from the heat and cool about to room temperature. Then only you pour the solution into 150 ml beaker containing 20 ml of ice water, or you can also add 20 ml of ice water into the mixture solution that you have in the conical flask earlier. Okay, this water must be mixed together with ice. Okay, must be mixed together with ice so that the temperature is below than 5. Okay, the reason why we do this is to force the product, which is the aspirin, to crystallize out or to solidify. So they will form crystals. So then only it can be separated. Okay, so that will be done in step 4. So once you cool the solution just now with the ice water and you mix it together, the crystal will comes out, and you have to collect the crystal by filtering under suction with a Buchner funnel, or you can use the gravitational filtration, but this will take longer time. Okay. And then the first once you obtain the crystal, okay, so below over here, the crystal is what you obtain on the filter paper. Okay, in the filter paper over here. So wash the crystal with 2 5 ml portion of ice cold water. So you want to wash it with very cold water. Okay, remember the water must always be cold, because if you're using hot or room temperature water, there is a chance in which that your aspirin, okay, will be hydrolyzed back, okay, into solution form, okay, and it will end up here, not on top of the filter paper. So that once you wash with the ice cold water, so number 6, using a spatula, place the crystal between several sheets of paper toweling, or you can put another filter paper on top and try to dab all of the crystal dry. Okay, so what you have until step number 6 or procedure number 6 is what we call as crude product. Okay, crude product. So this is not your end product yet, because the next step that you need to do is to recrystallize. Okay, you need to dissolve the crystal and recrystallize it again. So step number 7 is the recrystallization method starts, in which that the crude product just now will be put in the clean conical flask, and you have to dissolve it in hot ethanol. So you have to prepare an ethanol and heat it up, okay, but don't heat until it reach boiling point. Just the boiling point of ethanol is 72 degrees Celsius, so probably around 50 to 60. Okay, then as long as the ethanol can dissolve all of the crystal, so that should be sufficient enough. And I did not stated the amount of volume, because the volume will varies depending on the amount of crystal or crude crystal that you obtain from until step 6 earlier, in which that the volume needed, I would say, just enough to dissolve the crystal. So you add in small amount. So you don't add probably straight away 25 ml or 30 ml. So what you do is add maybe 5 ml first and see whether it is enough to dissolve everything. If it's still insufficient, then you can add another 5 ml. Okay, because if you add too much of this solution of this hot ethanol, later on when you want to recrystallize it back, you want to force the product to form the crystal, it will take a longer time. Okay, so step number 8 is to add warm water to the solution. So this has to be prepared earlier as well, in which that you have to heat the water, and also it doesn't have to be up to the boiling point. Okay, and the volume I would say to be equal to the amount of hot ethanol that you just add. So probably you just use 10 ml, so you add another 10 ml of this warm water. So step number 9, you wait until it cools down to room temperature, and then the crystal of aspirin will start to comes out. Okay, but under certain condition, okay, I've seen from previous experience, the aspirin still doesn't crystallize out. So you probably need to put the whole what do you call that, conical flask over here into an ice bath. Okay, so this help to the crystal to form, okay, the aspirin to crystallize out. Okay, and then step number 10 is to filter again. So filter the crystal again, and then you can dry it in an oven at 40 degrees Celsius. Then only you record the weight of the aspirin. So determine the percentage yield once you obtain the weight, the actual weight or the experimental weight of the aspirin. So the calculation over here, first what you need to know is the stoichiometry. So based on the two reaction that we have, the mole ratio is all is 1:1. So you have 1 mole of salicylic acid react with 1 mole acetic anhydride to be reacted with 1 mole aspirin. Same for the second reaction, 1 mole of salicylic acid will react with 1 mole of acetic acid to form 1 mole of your aspirin product. So the ratio is clear, 1:1. So that is for the stoichiometry. Okay, and then another 2 more information that you need to have before you can start your calculation for the yield is the actual weight of salicylic acid used, and also the weight of the product, the final product. Okay, the rest can be obtained like molecular formula for salicylic acid. This one you can find. Molecular formula for aspirin also you can find. That will be converted into all of these so that you obtain your theoretical yield. And what is your practical yield? Practical yield is the final weight of the product. Okay, the weight of the aspirin that you have done the recrystallization. Okay, so the percentage yield will be calculated as practical yield over theoretical yield times 100. Okay, and this is the results. Okay, will be written as you just put what is the percentage, maybe 70%, 80%, or 50%. So that is the yield of product or yield of aspirin. So now on to the material itself. Okay, there are several videos that you can watch, okay, for the synthesis of aspirin. Okay, there's one here with 40 minutes and 20 minutes. Okay, we will watch the 5 minutes videos.
Today we're going to make acetylsalicylic acid. That's the scientific name for aspirin. And you make aspirin by combining salicylic acid and acetic anhydride. We want to weigh out 2 grams. Okay. Actually, we have 2.027 grams. So record that number. Now we want to add between 4 and 5 milliliters of the liquid acetic anhydride. As you can see, there's a little of our salicylic acid in our whey boat. So in order to make sure we get it all in there, I'm going to pour the acetic anhydride here, swirl it around a bit, and then get all of it in my Erlenmeyer. And I want to mix. Next, we add 5 drops of concentrated sulfuric acid. This is making us an acid environment, and it will also cause the reaction to go a little faster. We want to heat this in a boiling hot water bath for about 10 minutes. After 10 minutes, you can see that the color has a sort of a yellowish brown tint to it. Now we're going to add 10 milliliters of cold water. Now we're going to put this in a cold water bath and allow the aspirin crystals to form. So you can see we have lots of aspirin crystallized in our Erlenmeyer. Now what we need to do is to filter our aspirin from the solution. And to do that, we're going to use a sidearm flask and a suction filter and this aspirator. The aspirator creates a low pressure inside our container here, and that will help gravity pull that water out and leave our aspirin inside the funnel. We need to put a piece of filter paper inside our funnel, and when we turn the water on, you see water's running down. That running water creates this low pressure here. We'll use just a little bit of water to make a nice tight seal, and then we'll pour our aspirin solution into the funnel. We're going to rinse the sides down. We want to make sure we get all of the aspirin into our funnel. You can see here we have lots of aspirin. Since we want to make sure we get it all, we're going to lift the filter paper into our beaker. And then we're going to rinse this with alcohol. This is ethanol, and we will rinse the crystals off of the paper with our alcohol. Now we want to dissolve our aspirin in the alcohol so that we can recrystallize. Recrystallizing will allow us to get larger crystals of the acetylsalicylic acid. Now we're going to add 60 milliliters of warm water. You see it gets cloudy? There's actually a little bit of crystallization that's occurring. You want to stir that. And now we get to wait again. We need to give this time for the crystals to form. So we're going to put it back in our ice water mix. We're going to weigh a filter paper. All right, the filter paper weighs 0.354 grams. So make sure you record that number. I'll place my weighed filter paper in the funnel and set up my filtering apparatus again. Now we can turn on our aspirator and filter. Next, we want to take out our filter paper with the aspirin on it and set it on a watch glass. Now we have to set it aside and let it air dry. Now we want to weigh our dried filter paper and aspirin sample. This is what one of the crystals up close looks like.
Okay, so from these videos, okay, you actually see there are two parts. First is the synthesis of the aspirin itself, and also the recrystallization of the aspirin. So this is more or less the general way of synthesizing any compound, even for inorganic chemical compound. You still have to do the recrystallization on the product form. Okay, one of the purpose of doing recrystallization, as she said just now, is to get bigger crystals. That's true. And another one is to further purify your crude product, because sometimes in the crude product there might also be impurities present. So normally the crude product will weigh more than your final product, which is the product that you obtain after the recrystallization of the crude aspirin just now. Okay, so another video that I want you to watch is this: how to calculate the percentage yield.
In chemistry, the amount of product you get from a chemical reaction is known as the yield, which we can measure in grams or moles. To be more precise though, we can use the terms actual yield to describe the amount we actually get when we carry out the reaction, and theoretical yield to describe the yield we'd expect to get based on our calculations. For example, if we reacted 2 grams of hydrogen with 16 grams of oxygen, then we should get 18 grams of water. So that's our theoretical yield, because 2 plus 16 equals 18. In practice though, it might not make quite that much. For example, we could end up with only 15 grams or so, and we'd call that our actual yield. Now, there's a whole range of reasons why we might not make as much product as we expect, but there are 3 particularly common ones that you need to know. The first is that the reactants might not all react. So at the end, some of the mixture will still be reactants. This could happen if the reaction is particularly slow, so it just hasn't had enough time to fully react, or because it's a reversible reaction and it's reached equilibrium. For example, if we reacted nitrogen and hydrogen to make ammonia, it wouldn't ever go to completion because it's a reversible reaction. So some of the ammonia would keep breaking back down into nitrogen and hydrogen. The second reason is that there could be side reactions, which is where the reactant reacts to produce a different product than the one that we were expecting. For example, if we were looking at the same reaction as a minute ago, some of the nitrogen might react with oxygen from the air to make nitrogen dioxide, instead of going to make ammonia like we wanted it to. And so we'd end up with less ammonia than we expected. The third reason is more simple. We could just lose some of the product during the process. For example, gaseous products can float off and escape. Or if we were filtering something, we might not capture all of the liquid or solid. To understand what we mean, imagine that we were using a filter paper and funnel to filter out a solution and separate the liquid and the solid. If our aim was to capture all of the liquid, it would be difficult because there'd be some liquid left in the beaker, some left on the solid, and also some left behind on the filter paper itself. And so we're not actually getting all of the liquid into the test tube like we want. Similarly, if we wanted to capture the solid, we'd also struggle because we'd probably end up leaving some behind when we try to scrape it off the filter paper at the end. The last thing we need to do is cover how to calculate the percentage yield, which tells us what percentage of the theoretical yield we actually got. To do this, we take the actual yield and divide it by the theoretical yield, and then we multiply it all by 100 to give us a percentage. So it can range from 0% if you don't get any product, all the way to 100% if we get all the products that we predicted. So if you think back to our reaction from the start of the video, where we reacted to 2 grams of hydrogen with 16 grams of oxygen, we predicted that our theoretical yield would be 18 grams. But we said that our actual yield was only 15 grams. So to find the percentage yield, we do 15 divided by 18 and then times it by 100, which would give us 83.3%. Or in other words, we got 83.3% of what we expected. Anyway, that's everything from this video. So I hope you found it useful and it all made sense. And hopefully we'll see you again soon.
Okay, so that's how you calculate the percentage yield. So the main thing is the percentage is quite easy, in which you just put the actual weight over theoretical weight times 100. But you have to know how to calculate the theoretical yield first. Okay, so that can be obtained by using the weight of the salicylic acid used, okay, and using the stoichiometry of the reaction. Then only you can calculate or expect how much or how many mole of the product will be formed. Okay, and another material that I have put here is this screen experiment. This one I will open, share another screen. Okay, so this is a screen experiment in which that you will have the ability to do the experiment on the computers online. Okay, so this is developed by RSC, Royal Society of Chemistry in UK, and also with collaboration with University of Bristol. So for you all to use this, okay, no need to, even though you see over here there's register or login, no need to register or log in for that. You can straight away go to the aspirin. Okay, so there are several screen experiment, but the second one is more on titration. Okay, select the first one, aspirin. So and there is 3 button over here. You straight away press quick start. Okay, no need to log in or register. This is for members, I think. You need to have the members ID and also password. So press quick start, and there are several levels. Okay, so you start with the first one, level 1, and then once you finish with this, you can continue with level 2, 3, and 4. So I will show example of what will happen when you click this level 1. So just click OK. Okay. So this is the interface will looks like. Okay. Along the way, they will provide you with information and also will ask some questions that is related to the experiment itself. So like this, you just click next. Okay, and there will be videos that you need to watch. So just press play. It will tell you some of the
Nearly all of us have
background
used aspirin at
background
some time in our life,
videos.
but not many people
So
know
you can watch
that for
it
hundreds
first.
of years, a related compound from willow bark was used to relieve pain and treat fevers. In 1899, a German chemist named Felix Hoffmann, who worked for a German company called Bayer, experimented with aspirin and gave it to his father, who was suffering from the pain of arthritis. With good results, he then convinced Bayer to market the new wonder drug. Aspirin was patented on February the 27th, 1900. In 1915, during World War I, the British wanted aspirin to help relieve pain for their soldiers on the front line, and so the British government offered a substantial reward to anyone who could help develop a manufacturing process. A Melbourne-based pharmacist did just that. Approximately 35,000 metric tons are now produced and consumed annually. That's 100 billion tablets every year. They're used not only as a painkiller, but also to treat fever, inflammation, rheumatism, and heart disease. Aspirin contains a carboxylic acid group, an ester group, and a phenyl group. Aspirin is created using a compound called 2-hydroxybenzoic acid by esterification with ethanoic anhydride under acid-catalyzed conditions. The chemical name for aspirin is 2-ethanoyl oxybenzene carboxylic acid. In this activity, you'll learn how to synthesize aspirin. You'll get to set up and run your own experiments and work out how much aspirin you produced.
Okay, so you have to watch the video before
Nearly all of us have used
sorry,
aspirin at
before the interface will allow you to proceed. Okay, if you haven't watched the video and you want to click next, it won't allow you to do that. So you have to watch the videos until the end, then only you can press next, then click finish. Okay, so you can review the lab book over here. So it tells you on all of the parts of the experiment. Okay, and then if you are ready, you can click next activity, click next, and there will be some question that you need to answer. And take note over here, down here, there are points. So if you answer this question wrongly, so the question, the points will be deducted. If you answer it correctly, then you'll get marks. Okay, over here it said maximum attempts 5. So I just put over here, simply put. Okay, just to show you what it looks like. Okay, then press check. So if there are answers that is wrong, you have to give the correct answer. For example, like this. Okay, and take note that the point just now has been deducted. Okay, so you can continue. Only if you answer it correctly, all correctly, then you can proceed. So you can click next activity. It will ask you to calculate the molar mass. Okay, so you can insert the number over here, and you can refer to the periodic table. So this is very interactive. This is molar mass. Okay, and you will go to measuring mass, synthesis, the mechanism, the precipitation, the drying, and how to calculate the yield. So, and later on you can download this lab book as in PDF version. So try to what do you call that, have a go at this screen experiment, because it is a substitute for you all, since you all cannot go to the lab and do it in person. So it is a good way to actually experience it. Okay, so this is, so once you're done, I think you can just close the tab. So, and if you feel like you want to repeat it again anytime, just open the link and redo again. Okay, so that is all for the material. One moment. Okay, so for the purpose of your report, okay, so to calculate the yield, you can use this info that I've give here on Google Classroom. So the actual weight of the salicylic acid that you use would be 2.04 gram. Okay, and the experimental yield is 1.67 gram. Okay, so you have to calculate the theoretical yield first using this actual weight of salicylic acid. Then only you can calculate the percentage yield of the aspirin product. Okay, so there are two more synthesis video over here that you can also watch, but the first videos, even though it is 5 minutes, I think it's already covered the whole procedure in a short span of time. Actually, the one that is 14 and 15 minutes, they doesn't edit it to this concise version. Okay, so but you can have a look to see maybe they did it differently or using different